talk about when the limit of a function does not exist at a point C. Before that, we're going to first just remind ourselves the definition of the limit of a function. So if f of x is a function and c is a constant, like a real number, like 3 or pi or 28.6, we say that the limit of f of x is L as x approaches c if, as x gets arbitrarily close to c, but not necessarily equal to c, the output of f of x gets arbitrarily close to L. And in that case, we write it shorthand this way: the limit as x approaches c of f of x is equal to L. Visually, this can take a lot of different forms, but basically what that's saying is as x gets close to c, as x is getting close to c, f of x, the output of the function, is getting close to the value L. And we see that in two different situations here. The difference between the picture on the left and the right is that on the left, it appears that the limit as f of x the limit of f of x as x approaches c is equal to L, and that's also equal to f of c. Whereas for the function on the right, the limit as x approaches f of x as x approaches c of f of x is equal to L, but that happens not to be equal to f of c. And in both cases, the limit does exist. We don't care about the actual function value at c, we only care about points close to c. And so in the first case, when it's true that the limit as x approaches c of f of x is equal to a limit, and that limit is actually equal to the function value at that point, we say that that function is continuous. That's the definition of continuity, which we will talk about more in a later section. And if it's the case that the limit of the function at that point is not equal to f of c, that's one way the function can be discontinuous. It's also discontinuous if the limit does not exist at all. But in this case, this is one way to be discontinuous. Okay. So our definition that we're using isn't extremely formal, but there is a more mathematically formal definition, and it's the following. For all epsilon greater than 0, there is a delta greater than 0, such that for all x not equal to c, when x minus c, the absolute value, is less than delta, then the absolute value of f of x minus L is less than epsilon. So for this class, you don't need to learn this for this class. If you take upper level mathematics, like say real analysis, you will be thinking about that sentence a lot. But for us, let's just say what it means for a moment, and then if you're interested, you could look at it more in section 1.2 of our book. And if you want to not worry about it for now, that's totally fine too. But let's just say what it means in this case. What that's saying is that when x minus c is less than delta, so we could pick, so for any epsilon we want, for as close as we want the output of f of x to get to the point L, if we say, okay, I want to get it to within 0.001, that means that there's some value, delta, we don't know what it is, but some small number, such that as long as x is at least within delta of c, then the output of f of x is going to be within epsilon of L. So for every epsilon, so this is L minus epsilon, L plus epsilon, there exists a delta such as that as long as x is within c plus delta to c minus delta, as long as x is within that interval and x is not necessarily equal to c, then f of x will be within epsilon of L. So let's think about some situations where the limit of a function might not exist for a value x equal to c. So one is if f of x approaches different values as x approaches c from each side, then the limit will not exist. So for example, if we consider the piecewise function f of x is equal to negative 3 for x less than 2, and f of x is equal to x minus 1 for x greater than or equal to 2. So in a piecewise function, there are different outputs depending on the interval that the input is on. So in this example, the output of f of x is negative 3 whenever x is less than negative 2. And we see that over here when x is positive 2, when x is less than 2, the output of f of x is equal to negative 3. So that's negative 3 down there. The output is negative 3 when x is less than 2. And when x is greater than or equal to 2, so from here on out, the output is instead the function x minus 1. So, for example, when f of x is actually equal, when x is actually equal to 2, f of x is 2 minus 1, that's 1. When f of x is equal to 4, that's also larger than or equal to 2, the output is 4 minus 1, that's 3, and so on. So we see that this is a place where the limit as x approaches 2 of f of x does not exist. And it does not exist because as x gets close to 2, the function output does not approach a single value. So there's no one single value that is approached. So here, as x gets close to 2 from the right, the output f of x does get close to something. It gets close to negative 3. But as x approaches 2 from the left, f of x approaches 1. It's getting closer and closer and closer to an output of 1. And so there's not one single value that is attained as x gets close to c, and so that tells us that the limit as x approaches 2 of f of x for this function does not exist. Another situation in which the limit may not exist is if the output of a function grows without an upper or lower bound as x approaches the value c. So one example would be the function f of x equals 1 over x squared, and f of x is graphed over here, 1 over x squared. So here, the limit as x approaches 0 of f of x does not exist, dne, does not exist. And the reason is that as x gets close to 0, f of x, 1 over x squared, gets larger and larger and larger and larger. So for example, when x is 0.1 or 1/10, f of x, that means that f of x is 1 over 1/10, or 10 squared is 100. When x is 0.01, or 1 over 100, f of x is 1 over 100 squared, 1 over 100 squared, or 100 squared is then 10,000, and so on. So as x gets closer and closer to 0 from either side, f of x is going to get arbitrarily large. So there is no upper bound in this case as x approaches c. And so we could say two things here. We could either say that the limit as x goes to 0 of f of x does not exist, or we could also say that the limit as x goes to 0 of f of x is actually equal to infinity. And I'll accept either answer. So the limit is not a specific real number L. infinity we don't consider to be a real number, but it is going somewhere. It is going to positive infinity. We could, in contrast, think of f of x equals 1 over x. And for f of x being equal to 1 over x, there really is no limit as x approaches 0 of 1 over x really does not exist, is neither positive nor negative infinity, because 1 over x goes towards positive infinity as x goes to 0 from the right, but 1 over x goes towards negative infinity as x goes towards 0 from the left. So here, the limit just does not exist as x approaches 0, whereas here, you could answer it in two different ways. You could say that the limit approaches infinity as x approaches 0, or you could say that the limit does not exist, and either would be reasonable ways to describe the situation. The last way in which the limit of a function may not exist at a point is if f of x oscillates as x approaches c without approaching a specific value. This is less common. One classic example is the function f of x equals sine of 1 over x. To see why that works in this situation, let's look at the function g of x equals sine of x. So this function should be at least a little bit familiar to you. Sine of x oscillates between -1 and 1, and at integer values of pi, the output of sine of x is 0, and at half values of pi, the output of sine of x is either positive 1 or negative 1. So for example, sine of pi over 2 is 1, sine of 3 pi over 2 is negative 1, but then sine cycles through those values, and so we keep seeing those values repeated. Sine of 5 pi over 2 is also 1, sine of 9 pi over 2 will be 1, sine of 13 pi over 2 will be 1, and so on and so on. So sine of 401 pi over 2 will be 1. Basically, whenever x is equal to 4k plus 1 over 2 times pi, the output of sine of x will be 1 in all of those cases, and whenever x is equal to 4k plus 3 over 2 times pi, the output of sine of x will be negative 1. So you don't necessarily need to know those two ideas necessarily. It's just important to understand that sine is oscillating between 1 and negative 1 forever and ever and ever. So now let's think about this other function, this f of x equals sine of 1 over x. So what does that function look like? Well, this function is also going to oscillate between 1 and negative 1. And for example, if we think of 2 over pi, or negative 2 over pi, or positive 2 over pi, both of those are going to have outputs of positive 1, whereas, for example, 2 over 3 pi, here's negative 2 over 3 pi, and negative 2 over 3 pi. Basically, we're just using the reciprocals of these here. So we're just looking at these reciprocals. This is going to have outputs of, those are going to have outputs of negative 1. So there's some oscillating here, and it's not going to be so different. Some oscillating, blah, da, 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 da. But then the funny thing happens when x is approaching 0. So as x approaches 0, these oscillations are going to happen more quickly because we're thinking about reciprocals of values like this. So if we think about, for example, 1 over 401 pi divided by 2, or in other words, 2 over 401 pi, and we think about that, that's getting close to 0. And similarly, 1 over 403 pi over 2, that's 2 over 403 pi. Those values are both close to 0, and they're also very close to each other. But the output of those values, the output sign of 2 over 401 pi is going to be 1, whereas the output of sine of 2 over 403 pi is going to be -1. So despite these two values are very, very close together, their outputs are really far apart. So we're going to have some wild oscillations in here, some wild oscillations between 1 and -1 in here. And there's no one single value that the output of sine of 1 over x approaches as x gets close to 0. So this tells us that the limit as x gets close to 0 of sine of 1 over x does not exist. And as I said, this is a less common scenario, so that's why we have sort of a strange function to help us illustrate it.